So far in the course, we have talked about converters containing only inductors, capacitors, and switches. We've ignored one of the other primary elements used in switching converters, namely the magnetic transformer. So for the next several lectures, we're going to discuss converters with transformers, what the basic circuits are, and how to model them and extend what we already know to understand the operation of transformer-isolated converters. There are a number of reasons to incorporate a transformer into a converter. One of the major ones is when safety requirements require that we have transformer isolation from the power line. Now, one way to do this is to put a 60-cycle transformer at the input of our system, but 60-cycle or 50-cycle transformers elsewhere in the world, these transformers are very heavy and large, and nowadays we generally try to avoid them whenever we can. The size of the transformer scales more or less inversely with frequency. So if we can build a transformer that operates at the converter switching frequency, say 100 kilohertz, instead of 60 or 50 hertz, the size of the transformer and its weight can be reduced by a very large margin. Another reason to use a transformer is when we have a large step up or step down of voltage. Suppose we had 100 volts and we wanted to make 1 volt. We could build a buck converter and operate it at a duty cycle of 1%, but such a small duty cycle may mean that the conduction time of the transistor is equal to the switching times of the transistors, and we find then that the efficiency is very low. Most of the time we're switching instead of conducting. So instead we could build a converter that includes a transformer that has a turns ratio and use the turns ratio to do most of the work of stepping down the voltage, and that converter then operates at a much higher duty cycle where the efficiency is better. Yet another reason is we sometimes build multiple output converters that supply multiple voltages. And these are simply additional secondary windings on the transformer inside the converter, and the voltages approximately scale by the turns ratios of the windings. Here's a diagram of a transformer that is a physical magnetic transformer. It has multiple windings, each with some number of turns. So winding 1 has N1 turns, winding 2 has N2 turns, and so on. And we've labeled the voltages and currents of each winding. Here the convention used with polarity marks on the windings is we're defining, for now, all the current is flowing into the respective polarity mark or dot, and we're defining the voltages as plus with respect to the dots. To understand how a converter works that contains a transformer like this, we need to first model the transformer and to write a set of equations that describe its behavior. What we're going to do is to employ this equivalent circuit model for the transformer. And so the physical transformer on the left is replaced with this equivalent circuit model on the right, where everything inside my dashed lines here is internal to the model and is modeling things that are going on inside the transformer. So we replace our physical transformer with this equivalent circuit model, and this equivalent circuit model has elements that we can solve using standard circuit analysis. So the equivalent circuit model we will use most of the time is this simple first order model that contains an ideal transformer inside these dotted lines, and then in parallel with one of the windings of the ideal transformer is an inductor that is called the magnetizing inductance of the transformer. Okay, so there isn't actually a physical extra inductor put on our transformer. This is built into the transformer, and everything inside this dashed line is an equivalent circuit that is modeling correctly the terminal equations between the voltages and currents of the windings. Okay, the defining equations of the ideal transformer we've seen before. The voltage of each winding divided by its turns is equal for all of the windings. So V1 over N1 equals V2 over N2, and so on. And this makes the voltages scale according to the turns ratios of the ideal transformer. The equations of the currents going into the windings of the ideal transformer is this one, and this is, again, we've seen before also. The sum of the amp turns flowing into the dots of the ideal transformer is 0. Now, in addition to the ideal transformer, we're adding one more element. This L sub m is called the magnetizing inductance, and its current, I sub m, is called the magnetizing current. The magnetizing inductance is actually real, and the way to see that is to do the thought experiment of suppose we connect something up to our transformer, like some AC voltage, connect it up to our primary winding, and suppose we disconnect all the other windings. So they're winding 2 and winding 3 here are simply open circuited. What do we expect this to do? Well, this is a real physical magnetic device. It has some number of turns of wire on an iron core or ferrite core. And if you have simply some turns of wire on one winding that is on a core, we would expect that to behave like an inductor. And the magnetizing inductance then actually models that inductance. So the magnetizing inductance referred to the first winding, where it's drawn here, is the inductance that you would get if you simply put N1 turns of wire on the core. The magnetizing inductance does behave as a real inductor. It obeys the voltage is L di dt, or in this case, V1 is Lm di im dt. And it has to obey volt-second balance. The average value of the voltage applied to this inductor must be 0. So we can apply volt-second balance to find the steady-state behavior of the circuits containing physical magnetic transformers. The magnetizing inductance also explains why you can't put DC through a transformer. So we can't, for example, apply a DC voltage, Vg, to our transformer, because at DC, the magnetizing inductance, being an inductor, has 0 impedance. Its impedance goes to a short circuit at DC, and it shorts out our DC voltage. And if we apply a DC voltage, volt-seconds won't balance on Lm. The magnetizing inductance is a physical inductor in that sense. It models magnetization of the transformer core. The transformer core has a BH characteristic. If you apply too many volt-seconds to the transformer core, it will saturate and the transformer will turn into a short circuit, which generally is bad in most of our converters. So if the applied volt-seconds on the winding is too large, what happens when you apply voltage is we integrate. So by Faraday's law, the flux in the core is given or proportional to the integral of the applied voltage. And as we apply voltage, we integrate up the BH loop. When we get into saturation, then the current in the windings in the magnetizing inductance becomes very large, and the magnetizing inductance essentially turns into a short circuit, which is called saturation of the transformer, and it's generally something we want to avoid. So then, we apply volt-second balance to transformers when we analyze converters that contain them. So the procedure here is that we replace the physical transformer with this equivalent circuit model that contains an ideal transformer plus a magnetizing inductance in parallel with one of the windings. And then we apply volt-second balance to this magnetizing inductance just like we do to any other inductor in the converter, and as we've been doing in the past. And understanding how the volt-seconds balance then is part of the analysis of the converter. Okay, we sometimes use the terminology transformer reset. And transformer reset is the mechanism by which the converter circuit makes the volt-seconds balance on the transformer. In many converter circuits, it's not easy to add a transformer. We have to add additional circuitry to make the transformer reset and get the volt-second balance to happen. So we're going to discuss that with respect to a transformer isolated version of the buck converter known as the forward converter, to understand how the transformer gets reset and how we can get the volt-seconds to balance. One last point, this equivalent circuit model is a simple first order model that is adequate for most things we're going to do in analysis of converters, but if desired we can further refine this model to model other things. So for example, if we want to model the resistance of the windings, like we've done in previous exercises for modeling losses in inductors, we can model resistance of the windings of the transformer by putting resistors in series with each of these windings. And in our equivalent circuit model then, these resistors appear basically at the terminals of the model, so in these places. Sometimes we model what's called core loss in the transformer, and we can do that by putting a resistor in parallel with a magnetizing inductance, the traditional way to do that. And sometimes we model what are called leakage inductances that are effectively series inductances in series with these windings. Okay, we're not going to model those in this course, but they do exist. They're a higher order effect in the transformer, but there are times where we need to include them. So in the upcoming lectures, we're going to use this transformer model to understand how some of the basic transformer isolated converter circuits work. We're going to look at transformer isolated versions of the buck converter and the buck boost converter. We will apply this model and understand the transformer reset, generalizing our ideas of volt-second balance and charge balance to include volt-second balance on the magnetizing inductance. I'll also briefly list some of the other common transformer isolated converters.